Okay, so today we're doing solutions of simple differential equations. We're going to learn how to do it numerically and analytically. Okay, so it's just a simple ones. So you need this handout right here. You need to download that handout, and you also need to annotate it and submit the annotated handout as part of your lab report. Okay, so let me just clarify exactly what we're going to be submitting. For your lab performance today during lab time, you're going to create 3 Excel files. So you'll need to submit those 3 Excel files. And you'll notice right here under settings, I'm allowing you to submit up to 3 files. Okay. So you're going to create 3 Excel files today, and that would be your lab performance. And then the last Excel file that you're going to create, which you create on your own, would be for your lab report. Okay. So item number 6 in the handout will require you to create an Excel file. That would be your lab report. And also, as part of your lab report, you're going to submit an annotated Word document of the handout. Okay. You can submit it here if you want to capture it electronically. You can submit it here. You can give me the hard copy. Okay. If you're going to submit it here, just leave a note. You can submit up to 2 files for this one. Let me see. So if you want to submit, you can submit up to 3 files. All right. So we're going to go through this document right here. Solutions of simple differential equations. Go ahead and download it and open it in Word. All right. Okay, so there are several places here where you need to answer some questions. And so I want you to put your answers in here, handwritten, okay? Especially the equations, you handwrite it, but the ones that you can type, okay? If you're gonna type it, put it like in a different color. That way I know that you've answered the question, all right? So this lesson has to do with integration of the differential rate equations. And what you're also going to learn is the basic strategy for using what are known as the Runge-Kutta method for numerically solving these differential equations. We've already done some differential equation solving last semester when we did the numeral method for the particle in a box. So you get to learn another technique this time for rate equations. All right. So let's start off with this first item here, first question here. Predicting how the concentration of a reactant or product depends on time, that's basically what you want to do when you're doing kinetics, will require us to solve a differential equation of, typically that's of this form. Okay, right here, dy dt equals a function of y and time. Okay, so derivative of y with respect to time is a function of y times time. Okay, so for example, y can be the concentration of a reactant R, and t is time. So if you remember, your first order rate law says the rate of disappearance of concentration of reactant R with respect to time is directly proportional to R raised to the first power, right? You've seen that in your review for your kinetics. So this is an example of a differential equation. Okay, so here your function of y and time is just equal to k times y being your concentration of R. There's no time dependence here, but in general, there could be some time dependence, but in this particular case, it's the simplest kind. It's just dependent on y. In this case, our y is a concentration of R. All right, so in this case, y is R. What's the expression for f of yt? The answer to that would be, it's just k times y, right? Or k times R. Right. Now, if you solve this differential equation, okay, when you solve a differential equation, you end up with a function. When you solve an algebraic equation, you say x equals some number, right? When you solve a differential equation, you get a function equals whatever the function is. So here, the solution of this differential equation will give you y as a function of time. And in the preceding example, okay, this was just given to you in your earlier classes, like in your freshman chemistry, that if you solve this differential equation that we have here, the answer you get would be R as a function of time is just whatever its starting concentration is times e to the minus kt. So this is the solution to your differential equation. Okay, so let's go ahead and derive that. So I want you to show a derivation in your Word document. So I want you to work it out on paper later, take a picture of it, put the picture on here. Or if you can draw on your tablet or your computer, you can do a screenshot. It has to be your handwriting though. Okay, don't take a screenshot of my video with the derivation. Okay, so let's do that. The traditional way of doing this is one of the easiest differential equations to solve. So if you start off with minus dr dt is equal to k times r. Okay, starting with that differential equation, we want to arrive at this expression over here, right? So the most common technique, if it works, if it's possible, is to separate the variables. What are your variables here? R, which is your y, and time. So put them on separate sides. So I can put, for example, I'm sorry, earlier in that question, it should be minus ky, right? Because I wanted, there's a minus here. So if I write dy dt equals f of yt, then I have dr dt equals minus k times r. So your f of yt here is minus k times y. All right, so anyway, let's rewrite this. Let's put the minus on the other side, okay? It doesn't really matter, but just for consistency. So we separate the variables. So we put dr, divide both sides by r. We want to put the r on the left side, okay? So divide this by r is equal to minus k times r over r. And then multiply both sides by dt. So the dt disappears from the left side. Okay, so the r disappears from the right side. All right, so we're just rearranging our equation there. Now what you do is you integrate both sides. What's integral of dr over r? You've seen this lots of times already this semester. Integral of d, or last semester and this semester. Integral of dx over x is natural log of x. So this is natural log of r plus some integration constant, right? Equals some constant, let's call that c. And on the right-hand side, what's the integral of a constant dt? I can pull out the minus sign. What's integral of k dt? It's just going to be equal to kt. So I'm just going to say minus kt plus another constant, right? So this constant right here and this constant right here, I'll just put them together into one constant. I'm just going to lump them all into one constant. All right. So ln of r is equal to minus kt plus c. Once you've integrated your expressions, you've gotten rid of the derivatives now. All you have to do is apply the boundary conditions. What do we know? At t equals 0, then r must be whatever its starting value is. R at time 0. It's going to be some constant. Okay? Constant. This is the value of r at time so this is your initial concentration, you would say. The value of the concentration of r at time 0. So when we substitute that, we're going to do substitute ln of r at time 0. So we're substituting for r naught equals minus k times 0 plus c. What's the purpose of doing a boundary condition? It allows you to figure out what that integration constant is. It tells you what C is. So this one tells you that C must be equal to 1. This is just 0, right? So that means C must be equal to ln of R naught. So now go back to the original expression. The solution we have right here. We're going to replace that C now. We now know what that C is. So we can say that ln of R is equal to minus KT plus C, which is ln of R naught. Okay. Now you can see right here, you've seen this before, that if you were to plot natural log of concentration of R, you're going to get a straight line, right? First order reaction. And your slope is equal to what? Negative K. And your y-intercept will be ln of R naught, right? So you've learned this one in your earlier classes or in the review that I gave you. So if you plot this on your y-axis, you plot t on your x-axis, you get a negative slope. So basically, you can see that this is an exponential decay, right? You've seen this. This is what you get when you have an exponential decay. Let's derive the exponential decay function from here. Let's actually express R as a function of time, okay? So I'm going to subtract ln R naught from both sides. So I have ln of R minus ln of R naught. What do I have left on the right side? It's just minus KT. Okay. Now, let's do a little review of logarithms. If you take the difference of two logs, ln of x minus ln of y, what do you get? This is ln of the ratio of x to y, right? So I can say that this left-hand side right here is ln of R over R naught equals minus KT. Now, if you want to get rid of the ln, what do you do? What's the inverse of ln? E to the x. So e to the ln of R over R naught is equal to e to the minus KT. Okay? So e and ln are just inverse functions. So now what do you have left? You have R over R naught equals e to the minus KT. Or you can say that R as a function of time is an exponential decay. It's equal to some initial value R naught times e to the minus KT. This is the equation that was just given to you without derivation in your earlier classes. This is how this is where that equation comes from. Okay, so an exponential decay is what you get when the rate of change of something is proportional to what it is. So, okay, so if you go back to the very beginning, we say the rate of loss of R is proportional to whatever R is. So the more R you have, the faster it goes. The smaller the R is, the slower it goes. Okay? Derivative is just the rate. All right, so what you have here, this expression right here, R equals R naught times e to the minus KT, is an example of what's called a closed form or the analytical solution. Okay, this very simple expression. That's why we went through it because it's the simplest ones you encounter. But oftentimes there's not a simple expression for the closed form solution, so sometimes you can't even get a closed form solution that you can write with a simple expression. So it's more convenient to get a numerical solution like we did last semester with the particle in a box. Actually, closed form solution is easy for particle in a box, but we illustrated how we can do something like that, right? So a numerical solution is just a tabulation of R at various at a selected set of t values. Usually we would specify a number of time values that are equally spaced intervals. Okay, so you make a list of t values for which you want to know what R is, and then you create another column where you have those values calculated numerically. Okay, and you can get that those numerical values without actually knowing what the analytical or the closed form solution is. Okay, so that's what we're going to learn today. And so to learn how to do that, let's suppose that your y at time t1 is y1 and its value at time t2 is y2. How are you going to calculate the slope of the secant line connecting these 2 points? Okay, so let's elaborate on that. Let's say, I know it's going to be an exponential decay, so let me draw something similar, right? Like so. Let's say this is your r versus time, or y. Let's do y. Let's make it more generic. So let's say y versus time, right? So this point right here is t1, and this point right here is y1. So this point is t1, y1, right? You specify the x, you specify the y. And this point right here, let's say this is t2. So this is y2. So this point right here, point number 2 is t2, y2. What if I want to know what the slope of the secant line? What do you mean by a secant line? That's a straight line that connects the 2 points, right? So if I have a straight line that connects these 2 points right here, okay? What's the slope of that line? Rise over run. So what's our rise? Delta y over delta x. So it's going to be y2 minus y1 divided by t2, x2 minus x1, but x is t. So t2 minus t1. So that's my slope, right? That's the slope of my secant line. So to answer this question right here, you can say this is what? y2 minus y1 divided by t2 minus t1. So I need to see that answer when you submit your annotated Word document. The Word document is due next week. So what if you know t1, y1, and m? How are you going to calculate for y2, the y at time t2? In other words, let's say, what if I know this one, t1, y1, and I happen to know what m is? Can I predict what this is going to be if I specify t2? Well, all you have to do is rearrange this, right? So let's rearrange that. I can say m is y2 minus y1 over t2 minus t1, okay? If I want to solve for y2 will just be m times t2 minus t1 plus y1. Or it's better to write it as starting from y1, I add to it, the change I would have to add would be m, how y changes over how t changes times t2 minus t1. Okay? So that's your expression right there. So your expression right here, y2 would just be y1 plus m times t2 minus t1. This equation right here is the basis for the general strategy for numerically solving differential equations that's known as the Runge-Kutta method. Okay? Runge-Kutta method. Basically, the idea is, as long as you just need to know what is it at this point in time, so you know t1, y1, and you have to find a way to get a good value for m so that if you use that formula and plug in t2, you're going to get a good value for y2. So you must first know your initial point and then you estimate m. So you have to have some way of finding m, and you do that using the expression for the derivative. Okay, so that you can solve for y2. Now, the simplest way of doing this, known as the first order Runge-Kutta method. This first order here has nothing to do with first order reaction. This is just the first order approximation. The simplest approximation you can make. This is known as Euler's method. Okay, Euler, E-U-L-E-R. That's not Euler. That's Euler. That's German. Okay. So here we approximate m by simply setting it equal to whatever the derivative is at point T1. Okay, in other words, what we're saying is in the Euler method, so the Euler method, first order method. So this is first order Runge-Kutta method, also known as the Euler method. What we're saying is that y2 is equal to y1 plus Rm is the derivative of y with respect to time, okay, at t1 y1, okay, multiplied by t2 minus t1. Okay, so this is our expression for m right here, whatever that derivative is. So that's the Euler method. And of course, that basically assumes that your graph is a linear graph, because this equation only works, strictly speaking, accurately if you have a linear graph. Or if your T2 is not that far away from T1, so if you look at the graph from T1 to T2, it's almost linear, then you have a good approximation. But so if, in other words, if you look at this graph that I just showed you earlier, okay, you can see if I were to use the Euler method for here, it's not going to work very well, because here's my slope right here. Okay, I'm going to draw a slope over. Let me redraw this one. Let me just draw another one. So let's just draw something like this. Okay. So let's say this is T2 and this is T1. If I do this, okay, I get a good approximation for my Euler method if my T2 is over here. But my T2 is over here, I'll be predicting my Y2 to be here. Okay? But if my T2 is over here, my predicted Y2 is going to be over here. So I'm going to get a, in other words, the Euler method, if you want to use that, you better be sure you use a small enough interval. Okay? And so that's not really a very good method, but it's a start. Okay? So dy dt is just the slope of the tangent line. Okay, remember, that's why I drew here. I have a slope, I have a tangent line. Okay, and so you're basically making a prediction. If your T2 is not far away from T1, then it's going to work. Okay, so we're essentially assuming that y versus t is a straight line between T1 and T2. So it will work better for very small time intervals. The larger the difference between the time between T2 and T1, the less likely it's going, the less reliable your results are going to be. So we're going to examine how the first order RK method agrees. I'm getting tired of saying Runge-Kutta, so I'm just going to say RK method. Okay. So the first order RK method agrees with the closed form. How well it agrees. Okay. And we're going to do that by creating a spreadsheet. We'll set it up like this. And so you can just type all of these, except for the ones that are in yellow, we're going to enter a formula. And then the ones that are highlighted in green here, we're going to calculate using a macro. We're going to write a Visual Basic macro. So let's go ahead and create an Excel file with these numbers. Okay. So what do I have? I need an R0. It won't let me. Okay. All right. I'm going to make this a little wider. So I have here R0. And I make this, line this up with the right side. R0, we're going to assume we have 1 mole per liter to begin with, our initial concentration. And then we're going to say our half-life is 10 seconds. You've seen this before. This is an exponential decay. So if your half-life is 10 seconds, what is our K? First order reaction, what's our K? What's the relationship between half-life and K? Remember? if R over R naught is 1/2, it's e to the minus k, then the t minus t naught is going to be half-life, right? So you solve for half-life, it's going to be equal to ln2 divided by k. Or you can say k is natural log of 2 divided by the half-life. All right, so if you know your half-life, so we're going to assume we know our half-life, so we can calculate our k. K will just be ln of 2 divided by the half-life. All right, so we're going to say k, if I know k, then if I know my half-life, my k will just be equal to ln open parenthesis 2 divided by my half-life. What would be the unit for my k? Half-life is seconds, so k is per second. Don't press slash here, because if you press slash, that brings up the menu. So press a space first and then slash seconds per second. Or you can put second raised to the minus 1 if you'd rather do it that way. Okay? Now, we're going to decide, we're going to calculate it in steps of the handout says. We're going to calculate, okay, so we just did initial concentration in cell B1 and then the half-life 10 seconds in cell B2. We entered the formula for K in cell B3 based on the half-life that is in cell B2. The next thing we need to enter is a formula for delta T, and it's usually represented by the letter H. If you ever take a course in numerical methods, textbooks in numerical methods usually use the letter H to refer to sampling intervals, okay? So delta T is the time difference between consecutive points. We're going to initially set this to be 1/10 of the half-life. So it's not going to be 2 because 2 is only 1/5 of 10, right? But we're going to change that later. But for now, let's make it 1/10 of the half-life. So I'm going to say H or delta T over here is going to be a formula. So what's my formula going to be? 1/10 of the half-life. So equals the half-life divided by 10. Basically, 1/10 of 10 is 1, right? Basically, what I'm doing here is I'm just what we're gonna do later is we're gonna change this to 1/5. So we're gonna make this interval bigger, and we'll see what happens. What happens if you make the interval size bigger? How badly does the results come out? Do the results come out, basically? Because we already know that smaller time intervals would give you better results, right? So let's just say we want to do one every 1 second, okay? You want to calculate R at every second. And then later we're going to do it at every 2 seconds, and we'll see what happens. Okay, cell B5, you enter the row where the initial concentrations are listed. If you look at this thing right here, you can see the initial concentrations are given in row number 10. You see here, row number 10 times 0, and then initial value of R is 1. And so T1 row right here, T1 underscore row, that's the name of the variable we're going to be using later in the macro to locate where the first data point is, where this initial condition is. So for the first step, we're going to say that's in the 10th row, okay? So let's go ahead and do that. You can say T1 underscore row for the first step is row number 10, okay? And then we're going to calculate it for so in row number 10, we're going to start with time 0 in row number 10, okay? Now, in row number 6, in cell B6, we're going to enter the number of steps, okay? This is the number of times that we're going to increase delta T. So when we do our calculations, all we do is basically, okay, advance the time, all right? And then calculate Y for this time. And then advance the time again, calculate Y for this time. Advance the time again, calculate Y for this time. So this is where you specify how many times you want to advance by an amount equal to delta T. So initially, we'll just set it to 1 for now. Okay, so number of steps. Number of steps equals, we'll just do 1 for now. So what would be my TMax? If I do it only one time, and every step I take is 1, how long will it take me to get to TMax? My TMax is going to be 1 second, right? So in general, what would be my TMax? Number of steps times delta t for each step, right? So this formula right here is just going to be equal to the number of steps times whatever delta t is for each step. We're always going to start from time 0, okay? So that's our TMax. So if I do 30 steps, what's going to happen? I get 30 seconds, okay? Each step is 1 second. If I only do 15 steps, I only get 15 seconds. So if I were to do like later, instead of doing it like every second, I do it every 2 seconds. Like if I enter 2 there, then it will take me 15 steps to get to 30 seconds. Okay, so let me just put this back to what it was. So 1 step for now, right? Okay, next, cell B7, enter formula for Tmax in terms of delta T and number of steps. We just did that, right? Tmax is just delta T. Did I start recording? Okay. Tmax is delta T times number of steps, right? And then adjust the number of steps so that Tmax corresponds to 3 half-lives. Okay, so now I want to calculate up to 3 half-lives. So if my half-life is 10 seconds, what should my Tmax be? 10, 20, 30. So I should have 30. So how do I make it 30? How do I make my Tmax equal to 30? How many steps should I take? 30 steps. Okay. So now you're going to save this spreadsheet. Give it your last name and then underscore and then Euler and then save it as a macro enabled file so that the extension should be .xlsm. So this would be a good time to save file, save as. I'll put this in the desktop. My last name underscore Euler, and this should be a macro enabled workbook. Okay, Excel macro enabled workbook, and then save. Okay, just to show you to you again, save it as, put it in your desktop, give it a name, and make sure the file type is macro enabled workbook. All right. Okay, very good. You're all caught up. Okay. So now we're going to create a VBA macro that will calculate R in column C using the Euler method. Okay, and versus time in column A. So first of all, I'm going to let me finish up my Excel file here. I should have row 9 would be my headers, right? So time, R exact, and R Euler. So time. Over here in column B, I can calculate the exact concentration of R using the analytical method or the closed form solution. This is the exact. And here in column C, I'm going to calculate R using the Euler method. Okay. So my initial value of time is 0. Okay. And this one here, I'm going to enter a formula here later. This will be the exact formula. Should be easy to do. But over here, what we're going to do is this should also be, oh, okay. Actually, I don't need to calculate this first part right here. Yeah, I do. Let's go ahead and calculate this one. What should this formula be for R? This is equal to R naught times EXP minus K. This is K times time, which is this one right here, right? And that should be 1. That's your initial concentration, the concentration of time 0. But I need to fix this so that I can copy it down to the other time. So what should I do? Which of these should I put dollar signs on? B1, when I copy it, I don't want B1 to change. So press F4 there. What else doesn't need to change? Should not change. B3, that's the value of K. It should not change when I copy that. A10, do you want A10 to change? Yes, because the next row, it will be 11, so it will be A11 in the next row, right? And here, for the Euler, this is just going to be initially whatever this is, right? So that's actually a formula right there. But the rest of this down here, we're going to calculate that using our macro. So I'm going to highlight that in green, okay? And these will also be calculating using a macro. So our macro is going to say, okay, let's start off at the first row, the T1 row, the first row, at row number 10. So the macro is going to say, okay, I'm going to increase it by an amount equal to delta T, and I'm going to put the value here. So that's my T2. The macro says my T1 is this, my T2 is this, right? And then I'm going to calculate Y2. And then it goes through a loop, goes through the next time it goes through the loop, it's going to say, okay, my T1 is now this one. I'm going to go to the next row and I'm going to put my T2 there. And now my Y1 was my old Y2. And then I'm going to calculate the new Y2. So this is how our VBA code is going to work. It's going to calculate this, increases the time, recalculate the new Y2. So when it's here, it takes this one as T1 and that one as Y1. And this is T2, Y2. And then it goes on here. It's going to take this one as the new T1 and the new T2 and the new Y1. And this is the new T2 and this is going to be the new Y2. So that's how the macro is going to work. Okay. So let's go ahead and write that code. Where's the code? Right here. So make sure we're putting the code in the right place. So create the macro by pressing Alt F11 to bring up the editor. Okay, so Alt F11. Okay, that brings up your macro. Okay. And then, do you see what I see? Okay, it's hiding some things that should not be hiding. Oh, I want. Let's see. Project Explorer. Okay, if you don't see this, open up Project Explorer, okay? By default, you should see this on your window. All right, so what you need to do at this point is, okay, press Alt F11, then create insert module, and then create module 1. But make sure you insert your module in your VBA project with your file name. So click on VBA project first, and then insert module. And this will create module 1 right here under VBA project. Okay, there's 2 VBA projects. The one that has the file name is the one you want to click on first, and then insert module. So now we have module 1. This is where we enter our code. Okay, so one thing you need to do first is type option explicit. This will help us later, because if we ever use a variable that we did not declare, it will flag it. And so this is a good way to minimize, easily identify bugs. But when you mistype something, misspell like a variable name, then it will not show up as a variable that was declared. And so you can easily catch that kind of error, okay? Because you all have a tendency to misspell a lot. So let's just type option explicit there. Okay. First thing we need to do here is define this variable called K, dim K as double. Notice I did not create a procedure. I did not create a sub or a function. I'm defining this outside of any sub, outside of any procedure or function. That means whatever this K is, it will be visible to all the procedures or all the functions. Okay, so this is available to all the functions and procedures in your module. Then I'm going to define, okay, a function dy dt. What is function dy dt? If I hit enter at this point, it's gonna just create a second line here that ends the function, just to make sure that your function actually does terminate. Okay, but this function, this is a function that I want to use to calculate the derivative. I can't use dy slash dt because I can't use slash as a part of a function name. So I'm just going to call it dy dt with no slash. Okay, and I have to, if I wanted to calculate the derivative, I have to tell it at what time do you want the derivative. So t1, and it's going to be a double precision value, double. When you see double right there, to minimize the possibility of misspelling double, just hit tab so you select it right away, comma. And I have to tell it, it might need to know what, in general, it will need to know what y is to calculate the derivative. It needs to know y and t, okay? So I'm going to say t1 as double. And I see the word double there. I just hit tab to pick it up. Okay, and I want this function to give me back a double precision value, a real number. So this function is also double, so as double. So that's basically what I'm doing here. Okay, this function calculates the derivative if you tell it what the time is and what the y is. Oh, this is y1 as double, okay? And then it will give you the value of the derivative. So what's our derivative? So just say dy dt, the name of the function, is equal to minus k. Where does it pick up minus k? The value of k? Somewhere, k is defined somewhere, okay, outside. So it picks up that value, multiply it by whatever y1 is. How does it know what y1 is? You tell it what y1 is over here. Okay, so it's not even going to need to know what t1 is, because in this particular case, it's simple enough that it doesn't need to know t1. It just needs to know what y1 is. But we're doing it this way, even though it doesn't need t1, just to make it more generic. Okay, so that's our function. And if you recall, all of these lines that start off with an apostrophe that are shown in green, those are just comments. It's a way for you to remember what these things do, okay? A way to document the code. Next thing we're going to do is we're going to define the procedure called Euler. So I'm going to type sub Euler, enter, and notice that when I type enter, or press enter, it gives me that opening and closing parenthesis and the end sub right here. So I enter my code between those two lines. All right. So K, first thing you want Euler to do is read the value of K from cell B3. If you look at your Excel sheet, okay, cell B3 right here is where your value of K is. So cell B3, read from cell B3. So you're going to say K, so make sure it's inside the sum, K is equal to cells, plural, row 3, column 2. Column B is column 2. Okay, so this is the rate constant in cell B3. Row 3, column 2. Okay. And we don't have to declare that K, because if you declare that K, you override the declaration of K outside the sum. Because you want that K to be able to pass through your function. Next, you want to say dim H as double. What's our H? H is our sampling interval. It's our delta T. Where is that in our Excel sheet? H is in cell B4, right? So we're going to say H equals cells 4, 2. Fourth row, So this is delta T in cell B4. Fourth row, column 2. And then we're going to define number of steps, dimension, dim number underscore of underscore steps as integer. So you all have a tendency to misspell integer. So when you see the integer already highlighted, just pick it up right away by hitting tab. Okay. Number of steps is integer. And then you say number underscore of underscore steps equals, where is it located? Cell B6. Let's see. It's in cell, number of steps is in cell B6. So cells, 6th row, column 2, column B. Okay, cell B6. What else do we need? Okay, remember we're calculating Y2 if we know T1, Y1, T2, and M, right? So we need to define all of these variables as double precision variables. So go ahead, dim T1 as double, dim T2 as double, dim Y1 as double, dim Y2 as double, dim M as double. Okay? You still with me? Now I'm going to define dim T1 underscore row as integer. Remember? Right here, T1 row, right here in row number 5 over here, column is row, which is row 10. This is the first row. Okay. T1 row for the first step is going to be row number 10. So I'm going to read it off from cell B5. So I'm going to say dim T1 row as integer. And I'm going to say that's going to be row number 10, right? And then I'm going to be dim, I'm going to define dim T1 row offset. That's just the row before T1 row. So let me go ahead and define that too. Dim T1 row offset as integer. This is one row before T1 row. Okay. And so T1 row offset is just going to be where T1 row is, cells 5, 2, okay, B5 minus 1. Okay, if you want, you can say T1 row also, T1 underscore row is equal to cells 5, 2. If you want to insert that, that's fine. Okay, that's just row number 10. B5 right here, okay? Okay, so what else do I need to do now? So now I need to go through the loop. So I have to dimension I as an integer. I is just a counter, okay? So I goes from 1 all the way to the total number of steps. So I'm going to go through a loop that says for I equals 1 to number of steps, number underscore of underscore steps. And so that we don't forget, make sure that every time you type a for statement, you immediately type the next statement so you know the end of the loop. And then everything that goes inside the loop, you just type in between those two rows. Okay? So what's my T? My first T1 row is going to be whatever T1 row offset is, I add 1 to it, right? So 9 plus 1. So my first T1 row is going to be row 10. Okay. And then I'm going to say T1 is going to be cells T1 underscore row, comma 1. What does this mean? This means, okay, first time through the loop, it's going to go, okay, it's going to say, okay, 9 plus 1 is 10. Okay. So it's going to say, okay, row number 10. Look at the cell in row number 10, column A, column 1. That's my T1. So assign that to variable T1. Okay. So I know my T1. First time through it, that T1 is going to be 0. Then I'm going to say Y1 would be in column C, same row. Okay, so it's going to be cells T1 underscore row, column C. So row number, column 3. So that's my Y1. Look at your Excel sheet right here. Okay, this is my first T1, and the corresponding Y1 is this one. All right, so this is T1 and this is Y1. And then the next thing it does is it says T2, let's calculate T2. If I know T1, how do I calculate T2? T1 plus the step size would give me T2. So it's going to be T1 plus H, right? T2 plus H. T2 equals T1 plus H. I know my H already. So I just add H to my T1, I get my T2. And then what do I say? What do I do now? I say, okay, go on to the next row, cells T1 underscore row plus 1. Go on to the next row. Okay, our current row, remember, is T1 row. So the next row is T1 row plus 1. And go to column 1 of that row, column A of that next row. And then put in that row the value of T2. Okay, so this one says, go to the next row. Okay, the next row is whatever T1 row is right now. You add 1 to it. That's the next row. Column A, oh, still column A, and put the T2 that I just calculated there. Okay, so right there. Then, so now I've calculated this, and I put the next T over here. Then the only thing I need to do now is calculate this Y over here, Y2. So how do I calculate Y2? It says, well, before I can calculate Y2, I need to know my M, right? So to calculate my Y2, I need to know my M first. So M is equal to the derivative of Y with respect to time, dy dt. This is where I call that function up here, okay? And I pass to that function the value of T1 and Y1. Okay, so this is where I calculate my M. Now that I know my M, my formula is, what's my formula for Y2? Y2 is just Y1 plus M times H. T2 minus T1 is H, right? So what I do now is I'm going to say Y2 is equal to Y1 plus M times H. H is T2 minus T1, and M is the derivative. Okay? And now that I know my Y2, where do I put my Y2? I put it in the next row in column C. So what I do now is I just say, okay, I'm going to say, put it in the next row, cells T1 underscore row plus 1, the next row, third column, so column C. And in that cell, put the value of Y2. And there you go. And that's it. So that's what this does. Okay? Now, before we do these last three calculations, let's just actually let's go to the Excel sheet now, so that this is a good time, by the way, to save your work. That way, you don't lose any work. Okay, so now let's go back to our Excel sheet and insert here a box that we can click on to run Euler. Okay, so insert. Let's just shape right here. I'll just put a square here, and then I'm gonna type RK1 here. RK first order method. Okay, and then what do I need to do with that one? I assign a macro to it. Right click, assign macro. What's the macro? Euler. All right, there you go. So if I did that, this is what you see. Only does one. Why does it only do one? Hmm? For one? It shouldn't. Let's see. Yeah, I'm typing some. I typed something wrong. Number of steps. I did not read the number of steps, did I? Cell 6 to cell B6. 30 steps. So where did I go wrong? Oh, this should be plus I. Sorry. Okay, this is plus I. Because we're going to go first 9 plus 1. That would make it 10. And then the next time it goes through the loop, it's going to be 9 plus 2. It's going to go 11. The next time it goes through the loop, it's going to be 9 plus 3, 9 plus 4. Okay, so this is where I made the mistake right here. It's not plus 1, it's plus I. Okay, so if I did that, see, it's doing it correctly now. 1, 2, 3, 4, 5, all the way to 30. Okay, so let's just highlight all of these so I can highlight them all in green. These are all calculated with the macro. All right. Now, if I did like, so let's say I get rid of this. Okay, this is how I'll check your work if you're doing it right. I'll change your number to maybe like 15 steps. If I hit RK1, I should only see 15. Okay. If I change this like to every 2, if I hit RK1, it goes 0, 2, 4, up to 30. Okay, so I'll put this back to divided by 10. Okay. So 1 to 15. No what happens here. Let's do some changes here, just so you can see. Okay, if I were to, let's say, look what happened. If I were to comment this out, let's say I don't calculate M and Y2 and I don't put the value of Y2. Okay, so if I put these apostrophes in front of these last 3 lines here before the next statement, look what happens. If I click on RK1, it's only calculating the times, it's not calculating my Y's. Okay, so if I remove those apostrophes, now it's going to calculate everything. All right, there you go. So I need to go all the way to 30. So I'm going to go 30 steps. Click on RK1. I have 30 data points right there. Okay, so that's how RK1 works. Good time to save now that I got it working. Okay. So answer the questions here. Oh, let's enter the correct values of R in column B now. Okay. And then in column B, let's calculate the percent error. So how are we going to do that? Column B, how do I calculate my exact values? I already have that here, so I can just copy that down, right? So I just double click here. Those are my exact values right there, column B. And column D, I can calculate percent error. This is the exact value. This is the correct value right here. And then column C, you have the values calculated using the Euler method, which is not going to be perfectly accurate. So how do I calculate percent error? This is equal to the calculated value minus the exact value, the Euler value minus the exact value divided by the exact value times 100, right? And so, of course, the first one has no error. But look at all these numbers. What happens as we move farther away? You're getting more and more error. You're building up errors, okay? And you'll notice they're all negative. What does the negative error mean? It's overshooting the drop, right? The Euler value is lower than the expected value. Why is that? If you look at your graph, okay, this slope right here is steeper. The slope gets less and less steep. So you're always assuming a steeper slope than the actual slope, okay, over an interval. So you're always going to go lower than expected in this particular case, in this very specific case. All right. So that's your percent error right there. What I'd like for you to do is, okay, what's the percent error after 1 half-life? Let's look at 1 half-life. Okay, if we go from 1, where's my half-life? Yes. Percent error is just the Euler value minus the exact value in parentheses divided by the exact value times 100. Okay. All right. So what did we say 1 half-life was? 10 seconds, right? 10 seconds is our half-life. Look at 10 seconds here. The exact value is 0.5. It went from 1 to 0.5. Look at our Euler value. It's 0.487. So you record that percent error right there in your handout. Okay. At 2 half-lives, what's the percent error? Second half-life, you go from 0.5 to 0.25. Another 10 seconds later, you get to the second half-life. And look at your error. It's bigger now, right? Minus 5%. Third half-life, you go from 0.25 to half of 0.25, which is 0.125. You got a bit even bigger error there. Okay, so record those numbers. And what else are you going to do next? Now we're going to change our delta t. So it's now a fifth of the half-life instead of 1/10. So this time, let's see what happens to those errors if we make our delta t bigger. So if you have a bigger delta t, what will happen to your errors? What do you think will happen? Well, let's see. Let's change our delta t. Okay. And then, so I'm going to change my delta t. Instead of 1, I'm going to make it 2. So it's going to be equal to 1/5 instead of the half-life. Okay. And now I'm going to hit RK1. And so here it is. First half-life is now row 15. Second half-life is at row 20. The third half-life is at row 30. And I'm just going to get rid of the rest of it. You're told we're not interested in the rest of it. So we just want to compare what happens at the first, second, and third half-life. So what did we get here? Is our error bigger or smaller at 10 seconds? What was our error before? 2.5%. Now it's 5%. Okay. This time because we're using a bigger interval. Okay. And the error at 20 seconds, the second half-life, they're looking at 10% error now. Okay. So what's the important lesson learned here with these last two things we did? Give me one sentence. In the Euler method, a bigger time interval would generally lead to bigger error. Okay. So if you want to use the Euler method, although it's simple, you have to use really small intervals. So let's create a chart comparing the exact R and the Euler R versus time. So I'm going to insert a chart. You can just do a data points, XY plot, don't connect the dots, and then select data, add. I'm going to do exact versus time first. So time is my x-axis. Y-axis is exact values. There it is. So that's my exact value. And then now add another to that. Add x values again is time. And my y values would be my Euler. Oops. X values is time. And my y values would be column C, the Euler. And you can see that in this particular case, your Euler calculation overshoots the exact value, right? Lower than the exact value. Now, I'm not going to format this. You make it look pretty. You should know how to format your graph, okay? So I expect you to turn in something way better than this graph. I want labels and everything. Okay, so this is a good time now to save your work. And this is the first one you submit for your lab performance today. Yes.
So if we change our number of steps, 15, it should only give us 15 data points.
Yeah. Like if I click here, it's going to give me more than 15 because so if I only want 15 data points, I change this to 15. But you have to get rid of what you had before. Get rid of what you have. Actually, let's get rid of these two. So that if you click here, see, it only gives you 15. Okay. In fact, that's how I'm going to check your work. I'm just going to delete stuff and click on the button. It should give me back the results, expected results. So save this and upload this to Moodle as your first file for today.